Okay, how many of you have gone through with the content now? All of you? I expected
So can you repeat what you told?
we had. How many of you have gone through with the content of week one? This is the second session for week one. Okay. Okay, then it would be good while discussing when we discuss the things ahead of onward lectures. Then it would be good. All of you able to catch. So, how many of you understood with the topic? Some span basis. Have you got the doubt on that? Is that clear?
So I got
Anyone?
doubt in 1.6 second question where we have coordinates and two bases given.
1.6. Okay. Question number 3. Is it?
So let me check one second.
Okay. Any other doubt related to the, yeah, any kind of activity practice except the credit in the lectures? How many of you understood with the word basis, span, linear independent, and dependent? Any doubt related to that? We'll discuss surely, but if you tell me that yes, I have gone through, I didn't understood, or you understood, you can explain me that. That would be it would be good. I will hear that. Okay, once I will hear this, then it will feel better to me that okay, you are following the lecture. Why? Because I am continuously emphasizing on it that if you'll watch the lecture and now we'll discuss today, will it will be clear more on topic.
So 1.6
So
question number one.
Question number one. Okay, okay, I will discuss that once I will reach to that topic. Yeah, 1.6 already discussed that. Okay, yes, Amit.
so regarding on that basis and dimensions is there, right? Can you clarify a little more details in that?
Yes, yes.
Basis and
Yeah, that
vector
is
space. I'm
what
getting
the today's
confused over there
topic.
actually.
Yes, I will. Yeah, I will discuss that thoroughly. I will try to be how much I can possibly discuss that to you can understand. I will try to that. Yeah, I will do the change of basis, which will not found difficult because change of basis is a bit difficult once you see the lecture 9. Change of basis. Let me present then. Let me present my screen. Yeah, this is one of the top topic, top topic of week one. Change of basis. This is the top topic of week one, which is all implemented, which will implement all the which will study within the week one. Sorry, lecture one to it. So let's start with the topic now. Yes, Ananya, I think asks the question one, how this could be. Uh, what is that? So I will start again and discuss a bit about it, then discuss the linear combination we have discussed. So last time we have seen that vector space, and still remain to discuss the subspace. Let's quickly do that. So I will go through with the axioms, or discussing with the where it is. Subspace is fine. This is vector space R2 addition property. Subspace of R2. Okay. Properties relative commutative accessory identity universe. Yeah, okay. So let's discuss that. Let me list out quickly the I will not say the vector space. I mean to say I will do with the R2 only. I mean to say I started right. I said that, okay, let me make it. I started. I hope who attended the session, I will start from there, because we have discussed a lot on the vector space. So let's say I said that no vector space. What is a vector space? I said that we have some space in that. Around that we'll try to play. That is what, like, as the real line it is. So as we have the real line, right, we can add the real numbers, we can subtract the real numbers, we can divide, we can play anything, and whatever we'll do between two real number, it will be within the line. That means if you think it a kind of set, if you think this R, this real line, this real numbers, collection of real number which represent a line, which we are representing as a line. Okay, let's say I am saying this is a set yes. Okay, so I took two element from this R. Let's say I'm saying this S, and another element 5. Okay, which is, I'm saying S is equal to exactly R. So when I am adding these two, it will be 8. 8 is also a real number. Okay, it is also a real number, right? That means we can say it belongs to S itself. Means whatever I will do the operations, even subtract, even division, okay, or even multiply, whatever I will do, it will be a real number. It will be a real number. Means I hope you can understand this sign. What sign is belongs to? Means this is that this number is a real number, belongs to that set. I mean to say this set is belongs to that set. Please just stop me if you are at any place you are not understanding. Please stop me. Okay, this is a request. So see that when I'm adding, subtracting, dividing, anything I'm doing, it's actually belongs to that set. I mean to say when I'm adding, I'm getting a number here 8. It reflect to a real number itself. It will fall in that set only. So it's very similar to that. I'm defining V, means I'm saying vector space where I said no, here is a representation I use yes exactly R. So I'm saying the same way R2, V is R2 I'm saying. Okay. For the example, to understand more clearly, I'm saying this set. This R2 is our V. Okay. I can use even in the place of wherever I'm using yours, I can use R. That is, I can totally find this, but I want to give you, a convincing way to get a flavor between the vector space and R2, because R2 is a vector space. Okay, to be clear, R2 is a vector space. Okay, this is a vector space. What it means that R2 follows all 8 axioms. We have discussed, right, 8 axioms last time. I can show you. I listed out all 8 axioms. I think, yeah, this is somewhere here. This one. this 8 axioms. Even I missed one in that, the inverse thing, that for AB there would be a minus A minus B. So I mean to say, I said this all, I that is not needed. It is not needed here. It should be a inverse one. There is a inverse thing is there. So means 8 axioms. Last time I have discussed that. So R2 actually follows that. I hope now I'm started from R2. I said what is R2? R2 I said no, R cross R, which means that the first element here I am representing two numbers in a bracket, which is called array. R2. So column matrix you can say. Hope you have seen, because all of your maths background, so you know it at least, that I am representing these two numbers here and here. Let's say 5 and 3. The representation I am saying, this is a representation column matrix it is called. So this one, for first one is coming from this R, and this one is coming from this R. Both are same. Both R are actually exactly are real numbers. Only saying to be the representation. These are all actually representation. Okay. These all are actually just a representation. So this representation, which is called a vector, it is called a vector, representing to your on the real, on the figure wise, on a pictorial format. So you can do like the first, this is your R and this is your another R, right? The first argument, okay, this is called argument. The first argument I am taking from this line, and the second argument I am taking from this line. And where is the both are actually here is representing the corresponding point. So you can say this is the corresponding vector. So if I represent it, it's represented like this, that this is the quantity of the vector and this is the arrow direction of the vector. Vector means a quantity and direction, as you know in physics.
Magnitude and
Same
direction.
meaning. Sorry.
It has magnitude
Quantity,
and
not
direction.
quantity. Magnitude, yeah, quantity, magnitude and direction. See, I am representing this 5 3, right? So it tells you I am moving in that direction, means this tells you, right, I am drawing a line in that way. And the top is actually the tip, the arrow sign is telling you that in this direction it is. Let's say I am saying -1 and 2. So what it means, that if I represent here, it would be somewhere here. Yeah, it would be somewhere here, or maybe better to be here. So see, this is here. And now if I will match these two, so how I always, let's say I'm starting from 0, not saying always start a vector from 0. So start a vector from 0. See, I'm matching basically this. See how it is going. So this is what the direction, right? This is what the direction tells you. In that direction I'm moving. So this tells you a magnitude, quantity, and the in that direction I moved. So that is your direction. A vector contains magnitude and direction. So magnitude will see that like now we'll calculate the magnitude. This is how the meaning of a vector. Let's week one is to as just understanding a direction, or maybe this is just a representation. We'll more understand in magnitude. We study the
Sir, your voice is breaking. I don't know if it is.
Sir, your voice is breaking, having glitch, sir.
I hope, is it better now? No, it's breaking. Glitch is there.
So it's still same.
Echo is happening.
Is there? Okay. Am I audible right now?
Yes, sir.
Yeah, very sorry. Actually, my thunder and heavy rain, because of that I'm actually continuously trying, but I'm not able to connect it. Sorry, very sorry for that. So let's continue quickly. Okay, so I was discussing vector, and this is what the representation of a vector, and this is how, no, means geometrically or in the visualization part. This is how we can say the matching or pointing. See, as you know, the coordinate system, we are able to point, but we are able to point it. Let me relate you on that. How it is, you studied, then it will be more clear even. The R2. All of you studied coordinate system at least. So in the coordinate system, right, you are able to draw some lines, okay, some points. Okay, this is how it is. Okay, if you let's say I have 2 points, I can find the distance between 2 points. Okay, this is how it is. In this is in the coordinate system. It's represented as a 1, 2, and 3, 4. I can find the distance. I can find a line which passed through this point, or maybe a line passing through these 2 points itself. I can find a line. This is the coordinate system we know. But see, what is the difference between this coordinate system and this R2 is, in this coordinate system, there is no meaning of adding two points. Okay, I am saying the coordinate system, you generally call it as a point, not as a vector. But here I am saying this is a vector. Okay, this is a vector. Okay, I am calling it as a vector here. This is called point and this is called vector. And the second thing is that there is no meaning of always saying or mean to say, uh, if you say it, if you match this point and this origin, so this you will call as a line segment. There is no meaning of saying to direction. But if you feel it here, suppose I'm, when drawing, I'm this from 0 to, I'm when I'm going to from 0 to this point, so I'm following a direction, no? So in the coordinate system there is no meaning of it. But when I particularly indicate this point, let's say this is 1 and 2, or maybe even 3, 1 and 4. Okay, 1 and 4. So that means from 0 I am going to that point. Okay, when I am going, it's follow a direction, so that direction I can say this is 1. And the third point is, there is no meaning of adding 2 points. Okay? There is no meaning of adding 2 points. But here we are defining an R2 to add two vectors, right? I can add v1 and this is v2, and I will get that another vector. So this is a basic difference. You can make it. This is a big difference even. There is no meaning of saying to be adding a point. I'm not adding a point here. There is no, in the coordinate system. There is no meaning. But in the vector space, we can do. That is what you can meaning. You can get the meaning of space. This is from a space where I can add, play, do anything. But here we can only visualize, draw lines, structures. This is what it's happening here. All of you are able to connect it. This is a big difference even to relate the coordinate, I means the difference between the coordinate system and the vector space. This is what's happening in the vector space. It's look like exactly the coordinate system, but it is not. There's a basic difference. Is the big difference. Somebody has asked the question, what is the difference between the coordinate R2? You can call it also R2, right? Coordinate R2, coordinate system, R cross R. But what is the difference? Big difference, a simple difference you can call. There is no meaning of adding point in the coordinate system, but there is a meaning of adding point in the vector space R2. Not only the vector space, there is no meaning of, if suppose I'm there is no meaning of scaling. I cannot scale this point, but there is a meaning of scaling. I can multiply 5 by this scale, multiply 5 a scalar, which is I'm calling it a scalar, and I can get a vector, scaled vector. This is what it is. There is no meaning of here multiplying a 3 by a point, but here it is. That is what the defining means. We are at in the vector space, we added plus, we two operations are there where v1 and v2. When I'm adding, it will be again in v. Okay, here our case is r2, this is r2. Okay, when I'm multiplying by a scalar a vector, it will be again in v. Okay, which is r2 I'm saying. Okay, and these are the axioms. The first, the second, the third axioms is there is a zero vector. This is 0 0 vector. Okay, 0 0 vector in v. And the fourth is there is a inverse. If I have, let's say, a vector ab, then if I have, if this is there, you have, then there exists another vector which, let's say, I'm saying this is our v. Okay, so there exists a vector minus b where the representation is minus a minus b, such that when we'll add this v and this, let's say minus b means I'm saying v prime is exactly minus v it is. When I add v and v prime means here v minus v, which you will get zero vector. These are the four. And the fifth, you can say the scalar time v1 plus v2, which you know already. No, this is we have like a real numbers, alpha time v1 plus alpha time v2 spread out linearly. 6, you can say if I have a alpha plus beta, two scalars, and I'm multiplying outside of simple vector, so it will again spread out alpha b plus beta v. 7th, you can say there is a not scalar 1 is already we know one scalar 1 is there. When I'm multiplying v with that, I will get exact v. Okay, 7. And 8th, you can say the associativity live. Let's say I have v1 plus v2 plus v3. If I suppose this is here it is, so I can first add the rest last two, then add the first one. So these are all 8 axioms. You can remember by your, these are playing thing in R itself. At least these all properties very much you have seen in the from 6th standard. Distributivity, associativity. These are some laws, right? These are some associativity, distributivity law, identity law. These are the identity law, very similar to inverse law. These are already you have studied in real numbers. So exactly followed that. So this is what the big difference in the coordinate system. These all makes big difference. So we have done this. So still remain to discuss the subspace. Let's quickly discuss that. So subspaces, we know, right? We have R2. So there is R2 is, I can take a subset, right? We have a set. We can take a subset of it. So I'm taking a subset like this, where how it is x and x, such that x belongs to R, right? This is a subset of R2. What it represent? Anyone? In coordinate in I want to represent it. Anyone can tell what it represent?
Vector space.
Vector space is fine. I'm saying the in the pictorial format, like in graph.
Let 1, comma 1 is in R2.
Geometrically, like I said R2 is your this representative, the whole R2. This is your R2. This is R plus R. This whole is your R2. This is a subset. This is a subset of R2. Very clearly, you can see the two coordinates is there. So yeah, both coordinates are same. What represent here in this graphically?
Line
A
from the
line.
origin.
Yes,
With
the
the
which is
slope,
represent a line which
one.
pass through origin. That is exactly. That is what it is. So this is a subset. Means I till now I didn't use subspace word. I am saying this is a subset. Okay, it is totally fine. So this is a subset. Now this R2, which is a set, right? R2, this R2 is a set where contain the number is vectors like this, or even you have this problem with. So see, I want to tell you again, I can represent exactly this one by this, okay, or even this. I rarely use, and you can say this is I will not use here, okay. This is I will not use. I rarely use, but I can use this one, or I can use most of the time like this. Any
Sir,
representation I will take. Sorry.
what this S is subset or subspace?
So I am saying only this. Yes, is a subset.
Okay,
Till now
okay.
I am saying this is a subset. But now I am going to tell you that what is a subspace. Till here, this is a subset. Okay.
Okay.
But this R2, I am saying there is a operation plus and dot is there. Okay. The two operation R2 have. Then it is forming a space. Otherwise, it is also we have like a sorry, R2 is also we have like a set. But I have given two operation in that. And then it become a subspace. So whatever the operation it is here, this is a subset, right? It will be inherent in that. This will, whatever the rules, this will follow the same rule. This will, this can also follow, right? Means whatever the operations are here in R2, these operations will also be applicable in this. And once these operations are applicable, this kind of subset called subspace. Okay? This kind of subsets are called subspace. See,
So
now when
basically,
I add
subspace
one,
is
yes,
basically
continue.
subspace. If I'm not wrong, basically subspace is combination of subsets.
Not combination of subspace, not combination. Don't use combination. Just a subset. Subspace
Okay.
is just a subset. Subset.
Okay.
That's all. Yeah, the inherent thing is already whatever you have, your parents have the. It will be anyhow. It will come to you also. So the same thing. The operations will be inherent in this subset. So this is called a subspace, but not all subspace. So there is one thing. Not all subsets are subspace. There is a particular rule. When a subset follows, then it will be a subspace. Otherwise, it will not be. Okay. So what is that rule? The two rules are there. One, two rules. Professor is using three rules. So let me tell you what exactly the professor is saying. Two rules. It's depend on. I think he is saying will you say the two rules? Yeah, these two rules. What are the two rules? Exactly from the 8 axioms, the first two axioms here, the first two axioms, if this first two axioms will be followed by yes, which is R2 already following. R2 is, this is already following. This is already following. But there is not surety that a subset will follow. I will give you example. It may not be follow. But a subset will follow only these two. Only these two. Rest all automatically it will be follow. Okay. Rest all automatically it will follow. Only if yes will satisfy these two. Okay. Any subset will satisfy these two. The rest all will be automatically followed by yes. Okay. So let's see what when I'm saying a subset is not a subspace. So let's say I'm making a subset yes one like this. Okay. See now. Let me list out the first two rules. V1 plus V2 should belongs to S1. Alpha time V1 should belongs to S1. These two. Where alpha belongs to any scalar which is R. And V1, V2 are elements of. So even I'm not V1 and V2 are elements of R such that this one is happening. Okay, and this one is also happening. If these two things followed by yes, then I will say yes is a subspace. If not, then not a subspace. Getting? No? What I mean to say, if these two rules, if yes1 follows, then I will call yes1 as a subspace. Otherwise, it will be just a subset. This is a subset already. It is very clearly. This is a subset of R2. But I will call it as a subspace when these two rules will be followed by. So even anyone can tell, is this following these two rules? Yes, one. Yes, one is following even the second rule or first rule. Any one of the rule you can choose. And is this following this one? Anyone can try it. Even help me to try it. If you are getting the argument. So let me do it. Maybe you are not getting. So what I am doing, so it says take two element of this set. Okay, I am taking one element v1 as x. So I can take any element. Let's say I am saying x is equal to 5, and the second argument is already fixed 1. So let's say v1 is this one, v2 is, anyone can give the second element?
3.
3 and
1.
3 and 1. Yes, because second argument is fixed. Only the first argument is a variable kind of. So these two element I took. See, I am saying element. Okay, once, so this is a difference. Okay, this is a difference. You can say a set contain these two element from this S1. When it S1 become a subspace, no, I can start calling this element as a vector. So this is a difference. When I will call this kind of representation as a this kind of representation, okay, as a element or a vector. So the when from where the set is, from which set it is taken, it have taken, that set become a sub vector space or a subspace, then I will start calling this as a vector. Otherwise I will call it as a element. Okay, so see, I am calling this as a element till now. Okay, so this is element. I took two elements. Okay, these two elements I took. See, exactly it is look like. Okay, now let's check this first condition even. So v1 plus v2, so pipe 1 plus 3 1, this is going to be 5 plus 3, this is 2. Okay, 1 minute, 1 minute, let me add it. 1 minute. Sorry. Okay, so when I added these two, this become 8 and 2. Is this element belongs to S1? When I added, is this belongs to S1? The question is,
Yes. Yes. Huh? No.
is
No.
this
No.
belongs to S1?
No.
No.
No, right? Here the
No.
second
No.
argument should be 1.
Second is 2.
It is 2. So even this is not following the first rule. This is the first rule. This is the second rule. It is not following that. S1 is not following. So it is just a subset. It is just a subset, not a subspace. Clear? This is what the basic difference. If you check for yes, I just made it no. If I make a this one set, let's check this to condition for yes. Okay, so let me take two element v1. So I am taking two element. Anyone can give the element of yes. This
Four.
yes 4 4, because both arguments are going to be same. I'm taking another myself now quickly. So yes could be any, x could be anything, x could be anything, right? This because x belongs to R, I mean to say. So yeah, let's say I'm taking x as a 5 5. So two vectors I took. So let's add these two, v1 plus v2. So 4 plus 5 5. When I add it, it become 9 9. Yes, it is belongs to yes. The first statement is true. So this is just example. You have to prove it in generalize, in general case. Okay, this is one example, random example I chooses, and it's following. You have to check it for general case. So you can prove it. I will
So
leave
both
for
rules you
you
have
to
to
check.
apply, right?
Sorry.
Both rules you have
Both.
to apply, right? One is alpha into
Yeah,
V1.
yeah. This is the first one is correct. So the second one is remain still. Let's do that. So I'm taking now scalar alpha, which is let's say taking 3, and even let's say I'm taking v1 itself. Okay, v1. Okay, 4 4. Now it says that alpha time v1. There is a dot, right? It's not visible because we generally don't write it. We generally don't indicate it here. So let's do that here. So alpha time, now alpha time v1, which is 3 4 and 4, which become 12 and 12, right? Yes, it belongs to yes, right? Both arguments are same here, or both arguments are same here. So it belongs to. So both condition actually followed by this yes. So that's why this yes is a subspace. It is a subset clearly, but along with this, this is a subspace. Okay, but this yes one is not. This is just a subset. Clear? All of you, is this clear? This subspace thing? Clear?
Yes, sir.
Yes, sir.
So let's move to now the I still remain to one problem on it. Exactly one problem. Let's do quickly one problem on here. Uh Nenne has asked on it, I think. So the first, see, it is exactly, let me make a screenshot of it. So it is actually from the eighth rule. The whatever the 8 axioms are there, no, it is, the question is related to that exactly, but it is very easy. I hope now see it's written as in a v1 v2 case here. It's written in the form of no v1 v2, but how we'll proceed with this kind of, how we'll proceed these rules by the examples or by the in general case, exactly way it is we followed. Okay. So if these 8 rules are written here, by this way you can, as just now we did, right? By this way you can contradict or prove, or at least reaches some argument, is this going to be or not. So like this example, in this example, it's given, see it is actually related to the subspace thing. See, it is said, let's say V is this, which is a subspace in R2, not subspace, subset of R. There is no need of it. Okay. R2. Okay, this is a subset. Is this closed under addition? Is there is zero element? There this rule. See, this rule is exactly the here. This rule. Yeah, yeah, yes, this rule. And the closed under addition. Closed under addition. What it means that closed under addition? This rule, this the first rule. There is a name for this. This is called closed under addition. This is a name it is given. This rule is called closed under addition. This rule is these are very specific. That's why the name is given. See, because of this, the whole subspace is decided. So that's why the name is given. This is called closed. This for this one, the second one, the name is given closed under multiplication. Why it is? Easy to remember, because the addition here, the addition is happening. And closed means what? I will tell you the whole word here. What is the meaning of closed? Why this word is closed? Closed means here, when I'm adding these two vector, it is actually line in the set. See, here it is. With the example, it will be more clear. When I checked S1, this is the your closed under addition, and this is the closed under scalar multiplication or multiplication. So now check here, what is the meaning of closed under addition? Means when I'm adding this, I am getting this vector, and this vector is not belongs to S1. What it means that closed means you can say this is not closed in S1, means this is not closed in the set. This is not closed in the set. That is the meaning of closed. Means when I am adding, after added, I am getting within the set itself. As here it's happening, but it is not happening for the S1 case. Similarly for scalar also, if you check for scalar, this is not true also. If you take 3 and the vector from S1, let's say the 5 1, I multiplied here 3 with 5 1. This is become 15 and 3, which is not belongs to the set S1. So this is not closed under S1. Sorry, not closed under scalar multiplication or multiplication. It is called closed under multiplication, or sometimes it is called closed under scalar closed under scalar multiplication. Okay. So this is easy. So the first one is called, is this closed under addition? Is there any zero vector? Is there any, this one is true? So is this true? Even we checked, right? But in place of this one, we did x and 1. This one we did. And here it is given this one. So this is not going to be. Right?
Yes, sir.
What about the second case? Is there any zero vector?
No, sir.
Is there any vector? Is there any element 0? Not. So here is there any element 0 element? When we add, when we'll add, it will be the same. So let's investigate even. Is there any? So we know. Let's take one vector from here. Let's take an element. Sorry. Let's take one element from. I am taking 1 and 5. Okay. This is exactly from V. Okay. Now it says 1 5, and I added something. It will be exactly, I added something and it will be exactly 1 5 the same. What it means that I don't know what is argument here. But let's assume something is there. So let's follow that. This is equal to, I send that vector to this side. So 1 5 minus 1 5. This means when I subtract it here, this is 0 0. So that means the empty arguments here, whatever the empty arguments are there, this tells you exactly the 0 0. But is this belongs to V? Is this belongs to our V here?
No, sir.
Anyone?
No.
No, sir.
No, this is not, because we want here 1, but here we are getting 0 0. So this is, there is no existence of such. Is this, now let's check the third rule. Sorry, this the rth statement. This R statement. So is this followed? Yeah, actually it will be followed. Anyone? Will that be followed? Yeah, actually this is going to be follow easily. The reason is,
Yes, sir.
here AB is a kind of scalar. So let's take AB. I am taking A as a 3 and B as a 5. I am taking a vector V, not vector, I mean element, which is, let's say, 1 and 5. Now A plus B V equal to 3 plus 5 V equal to, V means here 1 5, equal to 8 times 1 5, which is 8 and 40. This is the left side. Okay. Right side, let's do for the right side. This is the left hand side. Let's do the right hand side and compare both are same. We are getting the same or not. That's how it's way to doing it. Okay, A time, which is our 3, and V, which is 1 5, plus B time 5, and the V is 1 5. This is what, A V plus B V. This is the right side, is equal to this one, and this is 315 plus 525, and this is 840, right? Exactly 840. So 840 it is here, 840 is here. So left and right are same actually. Left hand side is equal to right hand side. So this is true. We are getting it. Both are same. So for the this set, the this is followed, but the main thing, it is not followed, closed under relation, and so I don't need it is. So that is what I said. No, I said what I said. If these two rules will be followed, then rest all rule be easily followed by this set S1 or any subspace. Why? You can see one example. Here this set is not a subspace, but see, it is passing, so it is followed the this one rule. Similarly, if you check this, all rules will be followed by it. Only the identity one, this one, these three will, it will not follow. So this is what the subspace case also. Subspace means only these two rules will be follow. Rest all it automatically it will follow. Only the most important thing is the first two. And I hope this examples make you clear with this, right? Very much. Is this clear to all of you? What's happening
Yes,
here?
sir.
How the subspace is here?
Yes.
So do a practice on it. Do some example activity is a very good example. Do some activity. Even you can ask in discourse or anywhere. If you do yourself, this will be more understandable. Okay, one. Okay, somebody is saying that PA question should be correct. Okay. Let's quickly see it. So let's start. If this is clear, then now, yeah, let's move on to now the span thing. Question number 7. This is this question, Ananya? Yeah, PA question 7. Okay. Our company manufactures two type of product A and B with the different material X of production. You got 3 units of material and X and 2 units of Y material. B products is this one. Each of the following statement regarding the vector representation of the okay, really independent. Let's discuss that now. It's Riemann. So we'll back to this problem. Let's quickly now discuss. Now let's discuss we discuss vector space, subspace. Now let's discuss the linear combination. We have discussed already linear combination last time. We have discussed that what we said that even we did one problem on it, that saying to be we have a 3 5 vector. Is this vector is linear combination of the vector 1 1 and 1 0, vector 1 1 and 1 0. So what it means that this vector 3 5 would be written as a some vector 1 1, sorry, some scalar 1 1 plus some scalar 1 0 or not. If this is written, then it is true. If we are able to, means we are able to get A and B. If you are not able to get A and B, then it is not. For example, if we check it, if we check, is this the 3 5 is linear combination of 1 1 and 5 5, linear combination of these two or not. So that means 3 5 is written as a time 1 1 plus a b time 5 5, and such ab exists or not. This is the question. So is this true or not? So you can assume itself assume this is true, assume this is true to get the value of a and b. And if you proceed with that, so this is 3 5 equal to a plus 5 time b, a plus 5 time b, both are same, right? A will be multiplied here, this is here it is, and then added. This is what it is. So a, this will a plus 5 by is equal to 3, and a plus 5 by, sorry, 5b is equal to 5. Both implies that 3 equal to 5. Is this true? Because left side
No,
is same, so that means
no,
3 equal to 5. This is not true. That means there does not exist a and b. There is a and b, there is no a and b exist such that means it is going to be there, means if this is become makes it true. There is no such a and b. If it is there, then surely we'll get a and b value, some value of a, some real value of a, some real value of, we'll surely get. But here it is not. We are even assume it true and we reaches a contradiction. So that means there is not such a and b exist. So that means here this vector is not a linear combination of these two. That's the meaning of linear combination. So we have discussed it last time very detailed. Now I want to use this. So there is a word linear independent and linearly dependent. Let me write even clearly. Linearly independent and linearly dependent. These two terms are there. So let's understand why professor started from here dependent. Any one of the way you can choose, because both are actually a contradicting thing. When it is will be dependent or when it is dependent. What it means that? The first thing is what it means that. Very simple thing is there. Let's say I have a vector. Let's say I'm saying a vector v1, which is 1 1, and v2 is 3 5. Even let's say even 1 minus 1. I have two vector. Think about the case is, okay, I'm taking the linear combination of these two. Okay, so that what it means that I'm taking a linear combination of these two means, so I'm not specifying when I'm saying I'm taking a linear combination of these two. That means I'm saying a general case. That means here a time 1 1 plus b time 1 minus 1, or let's say here a time, it means that here a v1 plus b v2 equal to this one. That is what the linear combination, right? Yeah, that is what I am saying. Is this vector a linear combination? Means a time this, b time this. So that is what here I am taking here a time v1 plus b time v2. This is called a linear combination of these two vectors. Okay, what is the linear combination of two vector v1 and v2? Means this is all linear combination. Okay, let me write in bold way. A time v1 plus v. This is called a linear combination of vectors v1 and v2. Okay, this kind of where a and b are real number, means scalar. A and b are real number, means they are scalar. Okay, I'm taking a linear combination of these two. Okay, so this is the definition of linear combination. Let's back to the definition of linearly independent. So what is linearly independent? I'm taking these two vectors, okay, and I'm taking a linear combination of these two, okay, and I'm making it equal to 0. I'm taking a linear combination of these two vectors, okay, and equate it to 0. Once I equate it to 0, okay, what I will get here? So when I equate to 0, I start solving. I will get the equation, no, a plus b. Here is a minus b vector will get. That means this is equal to 0, means a plus b is equal to 0. Finally, it will give a minus b is equal to 0. So this means that a is equal to 0 and b is equal to 0. So this is what it's happening when I'm taking a linear combination of these two and equate it to 0. I got that the solution of AB is only 0. Solution of AB is only 0 I am getting. So that means then it is called the vectors, this one and this one are linearly independent. What is the now definition? The definition is clearly a vector v1 and v2 from R2 is said to be linearly independent, okay, independent when linear combination of these two, when I'm taking linear combination of these two equal to 0, this implies A equal to 0, B equal to 0. Then I already it is written as said to be linearly independent. V1 vector and V1 and V2 are said to be linearly independent. When they are called independent, when I am taking linear combination of these two, they become 0. Let's see it in the different method also, different way. What it means that, let's see it by now the cases, let's see by the dependent case, then it will be more clear to you. So how it is, the dependent means I am taking a vector, let's say 3 and 5. Okay, I am taking a vector 3 and 5. Okay, let's say I am taking v1 is equal to this one. I am taking another vector v2 which is 15 and 25. I am taking these two vectors. Is there any relation between these two? Anyone?
Yes.
Multiple.
2 is 5 times
Yes.
of V1.
V2 is 5
Yeah,
times
v2 is 5 times v1, and that's the meaning of dependent. And that is here it's happening. What is happening here? Dependent means this v2 is actually depend on v1. In different way, v2 is actually we are getting by some scalar time v1. That's the meaning here, dependent. So the definition now you can build yourself. Definition is going to be for dependent. Two vector v1 v2 set to be dependent, okay, when v2 or v1, okay, v2 any of the vice versa, even you can write v1 as a 1 by 5 v2. So you can say v1 is dependent on v2. Previously you are saying v2 is dependent on v1. Similarly you can say v1 is dependent on v2. So it's going to be vice versa. Okay, so v2 could be written some alpha time v1. If this is happening, then v1 and v2 are dependent. So now let's see it here. See, I am getting here a and b 0. For let's back to the independent case. Let's back to here. When I am getting equal to 0, what it means that? It means that am I able to write v1 as some scalar time v2? Something is there. Am I able to write in the case of independent?
No, sir.
No, right? Because if I'm saying, so means here we are getting both are 0. If let's do it from here, let's proceed from this expression here itself. So it means that a time v1 is equal to minus b time v2. v1 is equal to minus b by a v1. But here we already got a is 0. So that means this is wrong, totally wrong. Sorry, here is v2. That means what? I am not able to write v1 as some scalar time v2, or v2 is equal to some scalar time v1. Not able to write in the case of independent. But here it is in the dependent case. Okay? Are you all of you are able to catch it? Is it?
Yes, sir.
I repeat it.
Yes, sir.
Clear, right? Because what is happening, the word itself tells you that two vectors are said to be dependent when the first one or second one is generated by the whatever the second one you have, means another one. But for the independent case, the first one and second one cannot be generated, or we cannot get here. What it means that here if we take the example, we have taken v1 as a 1 and minus 1. So v1 is equal to 1 I took, and v2 is equal to 1 and minus 1 I took. It's look like very similar, but you cannot do some v1 is equal to some alpha time v2. You cannot do. If you are saying this could be, so let's assume, okay, let's assume this is there. v1 is equal to some alpha time v2. What it means that? 1 and 1 is equal to alpha time 1 and minus 1. That means here 1 and 1 equal to alpha and minus alpha. This implies that alpha is equal to 1, alpha is equal minus alpha is equal to 1. Both implies alpha is equal to 1, alpha is equal to minus 1. This means that 1 is equal to minus 1. Is this true? No. So we assume that it is there, but we reaches a contradiction. That means these two is cannot be written as the some scalar time v2. Means v1 is not depend on v2 or v2 is not depend on v1. So that means v1 1 1 and v2 1 and minus 1 are independent. Okay, clear?
One query.
Yes.
In this whole competition, we will be dealing with independence or dependence? Yeah.
Competition means which competition?
No, not competition. I'm asking like basically like if we are if we go on forward, like some like basis another like will come, right? Eigenvectors previously. So there we will be using independent or linearly dependent equations.
So we'll use independent only. Because
Okay, sir.
dependence means you can generate, if you have a v1, if you have one vector, you can generate the second one. What it means? Generate means you can evaluate by some scalar time equal to, and you can get it. This is not much usable. The thing is independency. As you have a human, also we are men and women. We need a independence. Everywhere is independent. The same thing. Independence is more important, even if you say in the competition. The word of competition, you're saying. Because dependence means this could be generate this one, means using this is nothing but is this one a kind of, means geometrically see here what's happening. Independent means, okay, so even the best thing is visualization. The independent is I have one vector here and one vector here. This is independent. If you see that, even the best way is diagram. 1 1 1 1 is here, the v1 is 1 1, it is here, the 1 1 is, let's say here it is, and v2 is 1 and minus 1, 1 and minus 1. Okay, it is going to be 1 here and minus 1 is here somewhere. Even yeah. Oh, sorry, I'm making wrong. No, here is 1 and here is minus 1. That is what I said.
It is in origin.
So
Actually.
here is your 1 and minus 1. So here is v2. See what's happening here. See, it's making two directions, different direction. Both are actually, there is no. Now let's see, the case is what we took as example. We took an as example 4. So where it is.
4,4.
No, 4 comma. Yeah. 3. Sorry, 1 1 and 5 5. Yeah. We took 1 1 itself, and the second one is 5 5. So 5 5 is somewhere here. For our independent case, v2 we took this one for the dependent case. This is for independent case. So draw now. See, if you see it, this is exactly on the followed by that line only. It is just scaled up. This is the same line, just scaled up. But for the independent, see, for the independent case, it's two different vector it's give. For the independent case, two different vector you are getting. But for the dependent case, see what is happening. For the dependent case, one vector is here, the second vector is just scaled up. In the same direction it is. So what it means, that independence means it will give two different direction, and the dependent case, it's only tell you the same direction. Only one direction you are getting. So anyone can, then here is a very good idea it's coming also. What it's happening here? Anyone can tell beyond of it what's happening for the dependent and independent? Using these two vector, can we say something more? Using these two vector, can we say something more for the independent? Okay, even let me change with the color and make it green, because I am using the green one for independent. And can you tell using these two vector something is there? By mistake I have taken the v1 as the same, but don't think I can take 3 5 and something the same. I can take, it doesn't matter. Okay, by it's look like we are doing some set theory, but it is not there. Don't make it like that. Means to say, using these two vector, can I tell something? And the independent, I want more case for independent.
This
What is happening?
V2 is dependent on V1. It's 5 times of V1.
5 times of v1, right? It is. Even think like the way it is. If this represents line, suppose these two represent line, this is represent line, these two represent line. See what it's happening? These two lines are actually in different direction, right? These two lines are in different direction, and that mean line means here this your r is this, here this your r is, and using this you are generating, means this is actually representing whole r2. What it means that if I will think this one as one direction and this one as another direction, so your whole r2 is nothing but just a rotation of these two. The whole r2 is just a rotation of these two. What it means that actually in different way the linear combination, all possible linear combination. Okay, I am taking the linear combination. Okay, but I am making a set. Yes. Okay, I'm using the word it is. So let's say I'm making a set where I'm taking the all possible linear combination. Is this set comprehension is clear? Is this set comprehension is clear? This set tells you? This, yes, what it represents? This is a set
Subset.
comprehension. Subset is fine, but is this are you all of you able to understand this set comprehension? What it means? That it means that this is a collection of all possible linear combination, right? This is a linear combination definition. Clear? But here I
Yes,
used
sir.
any r. That means it tells you all possible linear combination. Correct? This set is your all possible linear combination. Okay. So if you take all possible linear combination, what it means that? It means if I take alpha is equal, sorry, this a is equal to 1 and b is equal to 2, so that means 1 1 plus 2 times 1 minus 1, that means here 1 plus 2 1 minus 2, which is 1 and minus 1 and
3 and minus 1.
sorry 3 and minus 1, yeah, that is 3 and minus 1. Let's represent 3 and minus 1 is 3 and minus 1 is somewhere here. Okay, 3 and minus 1 is somewhere here. Yeah. Similarly, I will change some a and I will change some b. I will get another. Similarly, I will change, I will get another. I will get another. Okay, I am changing a and b, I am getting all. Means I am getting here, 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 here. Everything I am getting. See the power of independency. What is happening here? I'm changing A
Understood.
and B, it's generating whole R2. So what is your S is actually, it is a subset of
Span.
R2 or exactly R2?
uh, R2.
Exactly R2, because I am changing now A and B. B is any real number, A B is any scalar. Similarly, I took 1 and B. Similarly, I can take any, I can take A is 0, B is 0, both. I will get 0 0 by using linear combination of these two. So here 0 is already there. Similarly, all and all, it will actually hold. Slowly you will get all element of R2. And this is the beauty of independent. If you take two independent vector and linear combination of these two, this will become this will generate a, means this will actually, this all possible linear combination is your exactly R2. So I am now defining, I am now giving, this is a different way. Okay, this is one thing. Have you ever thought that I am taking the linear combination of the dependent one? What will happen?
We will get a line through origin.
Okay, maybe here it is the same. Yeah. When I took the linear combination of these two, if you think, okay, let's do it. Some A time 1 1 plus B time 5 5. If you take it here, this will be A A plus 5B 5B, which is going to be A plus 5B A plus 5B. Both are argument are same. What it means that it is just line. It is, it is actually up and down line. So see, if two vectors are dependent, what is happening? It's just generating a line. But when it's independent, I'm taking the linear combination, it's generating whole R2. That's the beauty of independent and dependent. If I'm taking the linear combination of two dependent, it is just generating line. But when I'm taking two independent, is generating, means here all possible linear combination I'm taking, it's exactly R2, it's happening. All element of R2 you are getting. And that's the here now the definition I'm making. Independent and dependent you is understood, right? By geometrically, sorry, graphically you see, geometrically you are able to visualize it also. Now I'm giving the definition of span. Span is nothing but collection of linear combination of, I'm saying the span of, what is the span? Span of two vectors v1 and v2 is nothing but all possible linear combination of these two vectors. Let me change the color even if you're not able to visualize. Let me write here again. Span of v1 and v2 is linear combination, all possible linear combination of. So what we just now seen, this S is nothing but the span of v1 and v2, and that is your, this set S is your a span of 1 1 and 1 and minus 1 v1 and v2, which is telling me a kind of span. So this definition of span is nothing but this one. Span of two vector is all possible linear combination of these two vectors. This is all possible. This represent all possible linear combination. Is this clear, the span word, all of you?
Yes, sir.
Yes, sir.
So it's look like easy. It's look like it's easy, but the span is very big thing. Span is every, if span and basis is everything. So I will tell you the more. So let me discuss here quickly. So here is, so anyone can tell, I'm just writing the, you can tell me the definition now. Span of vector v1. Now tell me the That's it. Can you give me the set? Just single, in place of two vector I'm taking one vector, a span of v1. What is that?
1, 2, 2, 4.
Okay, totally fine. Can you tell me in this way?
All possible linear combination of V1.
So all possible linear combination of v1. Can you tell me in this this set notation form?
A times V1, A belongs to real number.
A belongs to real number. That's all. This tells you all possible linear combination of just v1 means linear combination means, yeah, that's just scalar time v1. Just scalar time v1. That is what here it's happening. All possible linear combination of v1 means just alpha time v1. So the beauty thing is, see that now I'm back to, I have independent. I started a two vector. For the independent, I took 1 1 and 1 minus 1 independent, and for the dependent I took 1 1. And now let me change a bit about, in place of 1 1 I am taking different. I'm taking 1 2. Okay? And this is v1, and the v2 I am taking, let's say 5. Again the 10 time multiply 5 times, so just 5 times this vector v2, 5 time multiplied was there, right? 5 times v2. So I'm taking the now the span of these two vector, we just know span of 1 1 1 minus 1 is a time 1 1 plus b time 1 minus 1. A b belongs to R. And we have just now seen when we took, this is whole R2. This is whole R2. We just now seen here with the graph. This is what it's happened. Okay, let's see that here when I'm taking the span of two dependent. See what it's happening. Span of this 1 2 5 10. When I'm taking a span of these two, what is happening? It is going to be all possible linear combination. So 1 2 plus b time 5 10. A b belongs to R. Okay. See what it. So if you solve these two, what is going to be happen this here? If you see it slightly what's happening here. It is going to be a 1 2 plus, this is what? This is 5 5 10 is nothing but
5,
5 time 1 2. So
B
here
A
is,
A1.
yeah, 5b 1 2. A b belongs to R. Okay. So what it means that? It means that 1 2 I am taking common, a plus 5b. 1 2 I am taking common, so it will be a plus 5b. 1 and 1 2 vector 1 2 I took common, a comma b belongs to R. What is happening here? Some scalar time the vector. Some scalar time the vector. So can you tell me? Can you relate with just now we have seen this? What is happening?
For only one vector. So
Only one vector we are getting. So what it means that when two vectors are dependent, it is
only one
nothing
vector
but
is impact.
only one vector, span of only one vector. I'm here took the span of two vector, which is nothing but the span of one vector. That's all. Because a time a plus 5b could be any real number, right? If you are writing a, b, any real number, so this is also saying any real number. So in place of this, I can write even. In place of this, I can write some c time 1 2, where c belongs to R. Exactly. Which is nothing but span of just the vector 1. This one. And this is what it's happening. I started with 2, but I reaches 1 with 1 only. This kind of cases. So two vectors are independent. That means, sorry, two vectors are dependent means actually they represent only, they are means span is nothing but only one of. This is the difference of independent, dependent. This is the definition you are using span also. See the mix of independent, dependent, linear combination and span. Four things we are looking combinedly here. And I hope all of you are able to visualize, even the connect with the definitions, what's happening independent, what is happening when it is independent, what's happening when it is dependent. See the spanning, see what's happening in the span also. So see the now also the what is the importance on independent and dependent. We are doing so many things with examples only, so that if you are able to catch. Now if you see the lectures, that's why I'm saying, if you watch the lecture, you already watched the lecture, you are able to connect more here, you are able to understand more. If you didn't watch, now if you watch, you will able to relate more. I'm also following the notation and a professor is following, because notations could be different sometimes, but I'm trying to follow the same notation so that you are able to exactly match. So this is the span. So span is nothing but the all possible linear combination of vectors. So I told you the span of two vectors. So similarly, this could be, so many things are there. So in place, so span is not only of span is not only of talking about two vectors. Span is of single vector also. We just now seen. Even span of finitely many, maybe three also, three vectors. Even maybe finite, till finite even I can write. Till Vn. Anyone can tell the definition here in the set notation form? I'm taking the span of n vectors combinedly.
And they are dependent.
All possible linear combination of V1. Let's say I'm saying A1 now notation. A1 V1 plus A2 V2 plus A3 V3 plus dot 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 AN Vn. Okay, where A1, A2, A3 dot 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 AN all are actually scalar, means real. So a span of not only one, two vectors is there, three vectors also there, four vectors are there, or any finite number of vectors also. But generally we in R2 we look at only one or two, maybe till three also. Now I will tell you something more. Now I will going to tell you the final thing, basis. Basis word is there, and also the word dimension is just one word is added. So basis is main thing. So now I'm going to talk about basis. I will tell you more here. I will tell you what's happening with the three vector with the basis, connecting to the basis also. Okay. So basis, see the word, it is basis, no, it is a base, it is a base. Okay. What is the meaning now here? Basis is, so I will start with the two vectors only. Let's say I have the vector same, the 1 1 and 1 minus 1, and we have seen that these two are independent. We have seen these two are independent. Okay, so if you're not able to remember it, we did it here already, we proved it here, how they are becoming independent. So these two are independent, we have seen. Okay, so basis is now just observation. Okay, just observation, try to observe, because so many things we have discussed. This picture, no, this picture is explaining everything. This picture is explaining everything. Okay, only just I will recall with the terms, with the word. I will recall with the word only. So what is happening? So I took these two vectors are independent. Okay. Now we talk about the span of also. Span of 1 1 and 1 1 minus 1. And we have seen that this is exactly R2. Right? I'm just collecting everything now here. You will just match what's happening and I will give the definition of basis. See, we checked, right? We from that is what I'm saying, recall the picture here. What we did, 1 and minus 1 here, the green one, these two vectors, it's actually generating all dots means all points. Okay? And I said no, I'm all possible linear combination I took of these two, which is actually representing all points. So that is your span, means what is happening here. Span is all possible linear combination of. This is what the definition of span we have seen just now. And this is, let's see again, I'm making the picture. 1 1 is here. And 1 minus 1 is here. Okay. Okay. 1 1 minus 1 is here. And all possible linear combination. So I can take A is equal to 0 and B is equal to also 0. So what it means that 0 time 1 1 plus 0 time 1 minus 1, which is will give 0 0 plus 0 0 is equal to 0 0, means here the vector 0 0. Right? Similarly, I will change the value. I will generate slowly all points. Means generate means I can obtain using only these two combination. I'm just took the combination. It is actually giving all. I'm just collecting all possible linear combination, which is giving the whole R. So which is nothing but this span is your whole R2. And that is the final word. If you are getting such vector, what is happening? If you are getting such vector which is independent, first thing is independent, and the second thing is span, means they are spanning. When I'm taking a span, generating the whole R2. When I'm taking the span of these two, it's generating whole R2. If these two condition is satisfied by any two vectors, then it is called a basis. Let's do an example and it will be more clear to you. I'm taking V1, a vector 1 0, and a vector V2 1 1. Now all of you do and let me know, is this independent or dependent? All of you try it.
Independent.
These are independent.
Independent.
How?
Because they're not multiple of each other. They don't depend.
This is dependent, sir.
They're dependent.
Because
Why?
because if you multiply, you will get V1 itself.
How which number you are multiplying? To
Oh,
where?
sorry. I was playing like V1 into V2. Sorry, it is not one.
It is very much clear. You cannot write V2 as alpha time V1. You cannot write.
Okay.
There is no such
Yeah,
alpha.
understand. Yes, sir. Yes,
That means these two are independent.
sir. Yes, sir.
These two are independent. Okay, now let's check the spanning thing. So that means we check the first condition, check the second condition, span. Let's check the span of. alpha times, or not, so it's alpha or a time 1 0 plus b time 1 1, where a and b belongs to r. Okay, this is the span. Fine. Check that this is generating vectors, means different vectors. Can we check it? Can we do it?
Is A0 plus BB.
So
A
yeah.
plus
Or if we solve it, yeah, that is what. If we try to solve it also, this will be more clear to you. So let's do the steps in the set itself. This is going to be a plus b, and this is just b, right? I just
Yes, sir.
solve the set a bit. What it means that, is this more visible in comparison? Here it is not visible, but here it is visible now, right? What it's visible? B is going to be
B is equal to
anything,
0.
and here is b is equal to, sorry,
B is equal to any value and A will be a separate
yeah,
value.
b assumes any value. Here is already b, a assumes any value. That means what it's happening, this represent, or this could be any r, this could be any r. This is also a, b, both are independent, mean independent, or sorry, a or b r could be any real number, right? That means this could be also represent it, it is a some case, right? 3 plus 5 is going to be r itself, 8 r. So this is also going to be, this could be any r, means both coordinates of the vector, you are getting this r also, this r also. What it means that, this is nothing but here it's generating whole r2. That is the meaning of, right? In the set notation form, I can write here equal to r2. Are you able to get it, all of you? Please stop me where you are not understanding. Please stop me where you are
Uh,
not understanding.
I understood this. Like initially what I did is A plus B, I assumed it is like A plus B is equal to 0 and B is equal to 0. Like that we can proceed.
We can
This one
proceed
only.
it.
Okay.
That
Okay.
is what. Even we can proceed also. We can. Here is
So my
what is
initial
happening.
value
A
is
is
in
equal to
origin.
0. In origin, you can get a is equal to 0, b is equal to 0. If you substitute here, you will get a vector. This is nothing but, if you substitute here is a is equal to 0, b is equal to 0, you will get 0 0 vector. Fine. Okay. Okay, fine. I can take a is equal to 1, or maybe when a is equal to 2, b is equal to 3. So what vector I will get here? 2 and 3 is there. You can match this. Sorry, it is going to be 5 and 3. Means here slowly you will change the value a and b, you will generate the vectors. And all, not only this will generate all vector of R2, all vectors. So that's why this set is exactly R2. But the question is now, you are doing maths to yes. I just given the idea, but we need proof. How we will prove that this span is exactly R2? How we will prove? The question is how we can prove. At least all of you able to get it, what is happening here, how we are getting R2. Is this clear? All of you are getting it, how we are getting R2. But this is a visualization, no? This is a visualization. Means I'm doing with the examples or something, but we are doing proof here. So how we will prove this is going to be R2?
Sir,
How we'll
just by
prove?
the way you wrote,
Mhm.
like here A belongs to R and B could be from R, that way.
Sorry, here is doubt you are saying. You are saying the proof.
So proof.
That is what. That is why you reaches to. Yeah, correct. That is what here it is. Even if this is a very simple step here. This itself from here. So if you are writing like this and you explain this, and from here you can conclude. Here you can write the word in the proof word. If you solve like this, even solve like this is fine. if you span is equal to this, and this is what it is. From here you just need to write a proper mathematical term. Okay, the term is observe that a plus b is going to be some c, right? So many real number, because a and b is any real number. Observe that, and observe that the here you can mean the first argument or coordinate. Okay, first coordinate, or you can say argument. First argument or coordinate is any real number, and second, again the coordinate or argument, also any real number. Okay, any real number. That means we can conclude, even see, this is, I have given the proof, even this is a good, but not a very much, it is not exactly the type of proof we used to prove in mathematics. But if you are writing proof like this, because we are checking here your argument, your understanding, so this is suffices, and we can give the full mark on here, because this is suffices. We want to know you are able to understand or not. But the, because here the course is, the subjective meaning here is why we given subjective, to check your understanding. Okay, to check your understanding, because you will apply your maths in some electronics. Okay, that's why we want only to check your understanding. We don't want a proper, means we need a proper proof, but there are two types of proof. You cannot relate to so many type of proof. This is just a observation and proof is there, but properly proof is a very different, which is professor is not also wrote. So we can even, using this one we can say, we are not very detailed proof we are not doing. So even this is enough, this is suffices to say that, because we are here is, we are giving the arguments, we are reasoning, we are making the reasoning, we are giving the argument, proper argument, that observe that this is the first argument is any real number, the second argument is any real number. So it's conclude that this set is whole R2. This is just R2. Even in the set notation form, there is needed, set equality is there, you need to prove, if you remember 12th maths. But from here we can conclude, okay, this is whole R2. That suffices, and also that's enough. I will tell you this is the proof.
This is span of a plus b, right?
Sorry, yes.
This first argument and second argument means a plus b is my first argument, second is my b, right?
This is your first argument. This is the first argument or coordinates. The better word
Okay.
is, let's use coordinate, because many times professor is using coordinates. So the first coordinate is any real number. The second, so this is your first coordinate. And this is your second coordinate. And by this observation, you can tell this is the whole, this set is whole R2. So it is the span is. So see, this set, this is span. This is span. So sorry, these two vectors v1 and v2, satisfying both condition, independent and spanning whole R2. So these two vectors are basis vectors. So these vectors are basis vectors. Okay, these vectors are basis vectors, or you can say these vectors are a form of basis, or you can say these vectors form a basis. Basis of what? Basis of R2. Why this is basis means, Using these two vectors, you are able to get all vectors of R2. That's why the base it is. Base means what? The pillars. You can see the pillars. You have a home, and your home is made on the pillars. The four pillars. If you, for example, let's say one room is there, four pillars needed. So if you say now in the nowadays the making of houses is what they will just make pillars and beam, and that's all. Adding the walls or building the walls is nothing, no mean. Even they used to just draw the pillars, okay, and at the last they will add the walls. But if this part is done, only just pillars, everything is done. Your house is almost made or created. So that you can say these are the base. That is what you used to say. These are the base. So basis means you can say the R2 is there. So R2. So you can say these are the pillars to make to create your whole home. Means home is R2. These two pillars needed, and these two pillars are actually, and this all others vectors you can say the wall. All other vectors are just a wall. Using these two pillars, between these two pillars, you used to make the walls, right? That is what using these two means. This two linear combination. By taking these two linear combination of these two vectors, you can generate all vectors of R2. You can create all vectors of R2. You can make all vectors of R2, and that's why this is called basis. This is a basis, okay? Because we just now seen this is a basis. We have also just now seen this is also another basis. So exactly not, this is following not your home case, because for home there are so many. We generally have the four pillars or two pillars, whatever the pillars we needed for the home. But here, not only here is one basis, this is a basis, this is another basis. So for R2 there are so many bases, infinitely many bases is there. You can check even. This is also a basis. These two vectors are independent. These two vectors are independent. You can check it. And if you check the span, these two are first condition is independent. Okay, independent. The second is span of these two is R2. Both are true. This will form a basis. Okay. This will form a basis. I hope the basis is clear, right? Only need to check two things. So could be there also. What is there? Let's say I'm taking three vectors. So will three vectors be okay?
No,
Even. Yeah. So yeah,
because
that's good
R2
thing.
contains only X and Y.
So sorry, three vectors means not, so you are saying three X and Y. So when let's say three vectors means I'm taking one zero, one one, and one minus one. Okay, I'm taking three vectors. Let's say these three vectors. This is v1, v2, and v3. Let's say I have these three vectors. Is these three vectors are independent? The first check. Even the question is this,
Yes.
is this a basis? Is this a basis?
No.
So what we need to check means a basis could contain three vectors also, but we will see in the upper dimension, means a head dimension, means when it is R3. So what is dimension? I will tell you now. So first check, is this vectors is independent? Anyone? Is these three vectors are independent or
Yes,
dependent?
sir. Independent.
Why it is independent?
Because they are not multiple of each other.
Okay, let's see that. You said not multiple of each other. Okay, I will give. I am giving the argument. We just now check these two are independent. Correct. We just now check these two are independent. But what about the combined case? But we are checking all three, and you can see that the dependency is not only two case. Let me give one more. If you are adding three vectors independent or dependent, what is happening?
They are dependent
Anyone,
on all three.
any of the vector may depend on these two. What it means that v1 could be written as some scalar time v2 plus some scalar time v3. If it is such thing is also happening, then it is dependent. These two vectors are dependent. Okay. Why the independent means any of the vector could not return. I discussed for the two vector, but what about the three vectors? Three vectors means this could be any of the vector could be written as a linear combination of other two. This is happening. Means any of this vector is could be as obtained by some, and this is it's happening here. What it's happening here? Let's check even. I'm taking, let's say this is v1. Okay, this is v1. Okay, we'll check it even. Even I'm writing v1 is equal to, even I will prove for v3. v3 is equal to, I will write some a time v1 plus b time v2. Okay, how what I will get here? What is going to be a and b? You can easily get it by solving this this equations. 1 0 is equal to a time sorry 1 1 1 minus 1 1 0 and plus b time 1 1. This is going to be a plus b, and here just b 1 and minus 1. This tells you b is equal to, or a plus b is equal to 1, b is equal to minus 1. So you got the value of b, you can substitute here, you can get a is equal to 2. See, so what it means that this 1 and minus 1 is nothing but 2 time 1 and 0 plus minus 1 time 1 and minus 1. Sorry, 1 and 1.
It is
This
dependent.
vector, this v3 is actually, this v3 is combination of these two. See,
Yes,
this is
I
what
got
is
it.
this v3 is combination. Yes, sorry.
Nothing. I just say yes, sir. I got it.
Yeah, so this is what is happening. So it may, so we can talk about 3 or more vectors also. But if it is happening, any of the vector is generated by the others, means linear combination of others, then it is dependent. So in R2, the result is there. The result is that in R2, 3 vectors, any 3 vectors, never be independent. Never be independent. They always will be. Always be dependent. Why it is? Anyone can argue why it is so? Anyone give the argument?
Because third vector is combination of both first two vectors.
Linear combination or even basis, no? Even if you remember, here the picture is explaining everything. If only 2 vectors are generating whole R2, that means any third vector, if you are taking somewhere, what it means that this third vector is linear combination of this one and this one. That is what it's happening, right? Because all vectors, these two generating all vectors. If you are taking any one in here, let's say this is v3. So v3 is nothing but, this is your v1, this is your v3. V3 is even, see, I don't know even v3 what is here. I'm just indicating, but it is generating all vector of R2. So v3 is equal to some alpha time v1 plus beta time v2. So any 3 vectors, v1, v2, v3 in R2 is always dependent. Even 3, 4, more than 2 is going to be dependent. By this argument, you can, if you are taking collection of vectors, collection of vectors which is more than 2, then dependent. You can, without saying to be argument, you can say dependent. The problem is when it is going to be one only, collection of 1 or maybe collection of 1 and 2, then you have to check, is this going to be, just now we have checked, right? The way it is, we have already checked. and we have given definition for 2 only, either 1 or 2. So if it is alone 1, alone vector is always dependent. So this is a single vector is always independent. Why? Anyone give their argument? I am writing V1. This is always independent. Anyone can give the reason?
Because
Because
you not only
Because
because it's along there, so it won't be dependent on anything, any other vector.
this is yeah, this is a good, yeah, it is, because dependent we needed, at least for dependent we needed 2 vectors, right? Then we can say it is dependent on some other. This is alone, so that's why it is going to be independent. And the and algebraically you want to prove it, you can prove by the way a times v1. I'm taking the all possible, sorry, or not only the one linear combination. I'm taking a linear. If you see the definition, what definition? Take the linear combination equal to 0 and find the value of a and b. But here is only a, and if a times v1 is equal to 0, v1 is non-zero vector. That means a is equal to 0. v1 is going to be in v1 is a vector, right? Non-zero vector. Non-zero vector means what? Zero vector is this one. Non-zero vector is any one of the argument in non-zero. This is a non-zero vector. So non-zero vector times some scalar equal to 0, then a is equal to 0. What it means that this is the definition followed by the independent case. If I'm taking linear combination equal to 0, when I'm solving, I'm getting a is 0. It is independent. By that case, even just now you said, no, this is alone. There is no meaning of saying dependent on which, where the second vector, there is no meaning of it for the alone one. So it is independent. So problem is for 2. If it is 3 or more than 3, then always dependent. If it is 2, then you have to check. Okay. Clear? I hope many things is clear in very short time. We are
Yes, sir,
doing
clear.
so many things combinedly.
yes sir, clear sir.
So dimension is remain the word. Dimension. I'm just trying to finish it because it's already 10. So only the change of basis is remain. I will quickly tell that. That is just a formula. So dimension. What is the dimension? Dimension is, see, in R2 we are doing R2. So dimension is, if you see the definition, number of what is the dimension? Dimension word is related to the vector space. Mean to say, what is the dimension of vector space V, of vector space V, vector space or subspace, you can say subspace V or vector space V, what is going to be? So what is dimension? The number of pillars, right? Number of pillars.
Number of bases.
For R2, how many pillars we needed? For how many basis vector? How many basis vector we needed for R2?
2.
How many vectors? How many
Two,
pillars?
two.
We just now discussed 2, right? 2 pillars needed anyhow, 1 1 and 1 minus 1. Similarly, so many things, 1 0 and 1 1. So many means so many bases are there. Either I can take these 2 or these 2. So 2 pillars anyhow needed. So that number of pillars, that is 2. Okay. I just discussed a subspace, if you remember, starting x and x, such that x belongs to R, subset of R2. We found that this is a subspace. How many pillars is needed here? Anyone?
2.
2 or 1?
Sorry. 1.
Why it is 1?
Because x will get common and it will be a line through origin.
Correct. That is what it is. It is line, just line. The vector it is, no? See, I can write this one as a some scalar. X is your any real number. Some scalar point, only one vector. What it means? I just solve one step. This set. This set, I just solve one step more. This is what I am getting. And what is this? Is a span representing a span, right? Span of this is nothing but a span of 1 1. Exactly it is. And see, it is span is, and in a span only one vector is there, and a single vector is independent. So number of pillar is just one. This is independent alone. It is, yeah, you have to check the number of pillars is needed. You have to check two things: independent and span. So span is span, number of span, here is the element is there, yeah, alone it is there, so it is independent. So both condition is satisfied, means independent thing and span by this vector 1 1, right? Single vector. So only one means one vector is generating this is tells you the generating, no, whole vector, this generated by only single vector. So this is only one pillar is there, so that means one dimension. So dimensions is nothing but number of pillars, means how many vectors needed to generate it, the whole. That's it. Okay. So many things we discussed. Okay, so a small thing is I will just discuss a small, the last change of basis, and we done the syllabus almost, because now it's going more than 10. All of you are getting bored also. So what is the change of basis? So very small thing. So even I will relate the previous one. I have just now seen 1 1 and 1 minus 1, and I have seen this is a basis element, right? This is a basis of R2. We just now prove it. We have just now seen it. These two are independent and spanning R2. I have also seen 1 0 and 1 1 is also a basis of R2, right? These two are independent and spanning whole R2. Okay, totally fine. Let's see that. I have a vector in R2. I just took a general vector. Let's say in place of example, let me take 3 5. Okay, 3 5. I didn't tell you there is one next thing is 1 0. This one 1 0 and 0 1. This is also independent as basis of R2. And this is a special basis. It is called canonical basis. You can remember always. This is canonical basis of R2. See the basis. What is the special thing? This is 1 0 and this is 0 1. Okay.
Okay, sir.
Okay, so here the name. These for these vectors there is no name. Okay, for these vectors there is no name. For the special case, which is this one, this is called canonical basis. Okay, so I am taking a vector 3 5. I can write 3 5 as a 3 1 0 plus 5 0 1, right? I can write like this. What it means that I can say A of 1 0 plus B of 0 1, right? Where A is equal to 3 and B is equal to 5. I can say, right? This is what it is. So see this 3 5, this vector is written as a linear combination of 1 0 and 0 1, correct? This is a linear combination of this basis, canonical basis, correct? Can be this 3 5, as this one is also a basis, this is also a basis. Can we write this one with respect this vector as a linear combination of this one, because this is a basis generate. What it means that can I write 3 5 as a some a prime time 1 1 as b prime of 1 minus 1? Can I do? Can I find a some a prime b prime? Anyone?
We can.
Yes, we can actually. I just solve one more steps in this here. That means a prime plus b prime is equal to 3 and a prime minus b prime is equal to 5. This is a system of linear equation. We can surely solve and we can surely get some a prime. We can let's solve it even. If I add these two, 2a prime is equal to 8, simply a is equal to 4 and b prime is equal to, we can substitute a is equal to 4, b is minus 1. Sorry, b prime is minus 1. That means if this is written as this one, where we can write where a is equal to 4 and b is equal to minus 1. See the differences. The same vector when I wrote in the basis of the here this canonical basis where a is 3 b is 5, when I wrote the same vector here with a different basis, I getting different coefficient here, a prime b prime. This is a prime b prime is equal to, a prime is equal to 4, b prime is equal to minus 1. And this is called the change of basis. I have this vector. I can think this, I can see this vector with the different basis also. See, I changed the basis. Previously, this vector, I am able to see on this canonical basis case. First, I am looking here, this has a different, where the coefficients a prime, b prime is different. This is called change of basis. This is called change of basis. So here you are looking it in the, and on the canonical basis. Let's look at the third basis also wrote, right? One another basis I have. Let's look at the 3 5 on the basis of the this one 10 and 1 1. So some a, or even let's say alpha 10 plus beta 1 1. I just try to look at with respect to this basis. And let's solve it here. What is going to be alpha beta? So this is 3 5 is equal to alpha plus beta, and this is beta. And if you solve it, beta is equal to 5 and alpha plus beta is equal to 3. This will give alpha is equal to minus 2. So here, if I'm writing here, this is as some linear combination of 1 0 and 0 1. So where alpha is 5 and beta is, sorry, alpha is minus 2 and beta is 5. See, so many representation, no? So many things are there. Same vector, sometime, see here the difference. Here is alpha is different. Here alpha is different with comparison of here a 3. Here is alpha is 2. Beta is 5 here. The second here, the b is here. It is 5 here the same, but here it is changed with respect to this one. Here see it. B prime is different with respect to this. Here A's prime is different. So many representation, no? With the same, I am looking same vector with different bases. This is called change of basis. So question is now the question. Now the thing is how the question would be created. Think the way it is how the question is. Let's say the vector 3 4 is 3 4, or even let's say 3 5. Consider the vector 3 5 with respect to the canonical basis. Consider the vector. Consider 3 5 with respect to canonical basis. Find the, in subjective form I am saying, find the change of basis. Change of basis where basis is, I am writing basis is even any vector. Let's say here is 1 0, basis is 1 0 and 1 1. Find the change of basis with respect to this basis. So
One
what
query
your
here.
answer is? Yes, yes.
This 3, comma 3 and 5 is it's a vector or it's a scalar multiple? A and B, right?
Sorry. 3 and 5.
This, yeah.
This is a vector, right? This is a vector.
Okay.
This is all I'm writing. This all 3 5 is a vector. This is a vector notation is there, right? This is a vector notation.
No. I'm asking like your multi, like A and B are there. No, initially from starting, if you go there, it was like it's like
It's look like
scalar multiple.
some, yeah, it's look like, but yeah, it is. So that is the beauty of canonical basis. This is it's you are confused because of, yeah, or not confused. You are just hallucinated here because of this canonical. This is a beauty of canonical basis. Canonical basis is whatever the coordinates you are looking. No, this is we have like a some scalar time, the same scalar time, this one with the this is your vector 1 0, this is a vector, so scalar time this vector, scalar time this vector
So
0.
you're multiplying basically, if I'm not wrong, as per me. So for canonical basics, if suppose they are asking or considering, you are multiplying a vector with the canonical vectors. Am I right?
That's all that's totally all.
Okay.
Yes, that's all. If I'm saying the vector this one and saying with respect to canonical basing, this is nothing but this is your combinations. This makes your combination, the itself, the coordinate itself make the combination. So this is the beauty of, that's why it is the name, special name is given canonical. Clear? And other, with respect to others, it is different. And now see the question. Consider the vector with respect to canonical basis. That is what it's happening. That's why the question I wrote with respect to very similar coordinate basis. I didn't wrote even because it's telling that 3 5 is nothing but 3 times 1 0 plus 5 times 0 1. It's very obvious now with respect to canonical basis. Find the change of basis with respect to this basis. So your answer is going to be the change of basis is, we just now find 1 0 and 1
A
1.
equals to -2 and B is equals to 5.
A is equal to -2 and B is equal to 5. Alpha, in the term of alpha beta we wrote, we can write here B is equal to 5. The term of
Sir,
A and B.
can you solve the questions professor has given in the lectures? There was one different type of question.
On the same change of basis.
Yes, sir, in lecture.
In lecture which?
Yes, sir, 9th.
Okay, so this is what it is. I have, I think I added a
Sir, it will be
tutorial
in the
on it.
last.
So I added a tutorial on it. Please see it. Yeah.
Yes, sir.
Find the
So,
coordinates. Yes.
in this, I
This
have
is
doubt that in the first question, it's written find the coordinates of V1. So here we made the linear, uh, like we made the equations, and in the second one, we are using V coordinates as A and B. There, I'm confused.
no. So here is A is this is the first question. This is the second question.
Yes, sir, I did that. But in the second question, where it is find the coordinates of b is equals to 1, comma 2,
Hmm.
then basis with respect to basis. In that question, we are
Uh,
first doing the we
yeah,
are
A time.
finding another
Wait.
vector.
Yeah, correct. You are getting the answer. It is orally right. You can do orally. What is the answer you are getting? A is equal to
Uh, so no, sir, there we were using this v vector as a and b. Like we were using one as a, two as b.
A,
Mm,
yeah, one as A and two as B.
yes, sir.
No.
That's where I'm getting confused why we are doing that.
Oh, okay. Okay. So what is happening here? The question is, I have 1 2 vector, and it says change. Do the change of basis. The B question is I'm writing. The change of basis is says the basis is 1 2 and 2 3. The professor is asking, do the change of basis with respect to 1 2. what it's there here. See, the coordinates of v is 1 2 is given, the vector v coordinates. So see, this is itself. So let me tell you the coordinates. So 3 5 3 5 with respect to the canonical basis, with respect to canonical basis, 3 5 itself we having like a coordinates, right? These are called coordinates. Even these are called also linear combination. Here these are called coordinates. So whenever such thing is written, no, so it means that it is coordinates of a vector v is given like this. That means this vector is given with respect to canonical basis. Okay. So here it's a professor said that the coordinates of the vector v is given 1 1 2. It means that this vector is written as a nothing but with respect to canonical basis, 1 time 1 0 plus 2 time 0 1. Okay, this one is here, this 2 is here. That's why it is called coordinates.
So sir, that way is written in the first question also, but we made the equation there. Why we did?
So we have to make it. No, so even I didn't tell you the solution. I said what meaning of coordinate. I told you just meaning of coordinates. Till now I didn't solve it. You have to solve now. But it means that I have to solve the vector 1 2 is equal to some a time 1 2 plus b time 2 3. And the question is asking, that is what here we have to find the a value and b value.
Yes sir, I already did that. I got. Wait.
Sorry. So is this clear now? So here your answer is going to be a is equal to 1 and b is equal to 0, right? Because it is very obvious it is.
Yes sir, I did that, but in the first question we were making the equation, and in the second question we are using this vector as a and b. Then we are doing some other thing which was
No,
confusing.
in the first question also it is the same. Why it is a bit confusing? Let me do the
Sir, I
first
mean
question.
first question is the 1 and second question is 2. Not, I'm not talking about the a and b.
Oh, sorry. Here it is in the second code. Sorry. This one is. Okay, here it is. You are saying. Find
Yes sir.
the coordinates of v1 2 in the basis of this one. Okay, with respect to the basis of this one. See the here it is beauty now. So what it means that now this is a good question even. That is the more deep thing, not deep, condensed thing in the change of basis. What it means that, let me write here. That is the question, right? That is your question. Am I able to get your question
Yes
now?
sir.
Okay.
Yes sir.
So here is question is find the coordinates of v in the basis of this one with respect to the basis of this one. What it means that? It means that this 1 2 is given the coordinates with respect to this one. Here the find the coordinates of v with respect in the basis of this one. Coordinates with respect to this one, what it means that? It means here this 1 2, this vector v is your 1 time 1 1 plus 2 time 1 minus 1. If you say what is your vector, this is your vector. This coefficients actually called coordinates. That's why I said no coordinates. So coordinate with respect to this basis it is given. So that what it means that a time 1 plus 2 time 1 minus 1. Your vector v is, are you able to catch it? No.
Sir,
No.
this is the same language given in the first question, but there we made the equations.
No, this is given with the different here. Find the coordinates in the basis. Okay, find basis with respect to the basis. No, here is with respect to what. See, here is what it's happening here. Whenever this one is given, this means here this one means one. It says that coordinates of v is given as a 1 1 0 plus 2 0 1. Find the coordinates of v in the following basis. Here the vector v is given. Here this vector is nothing but this one. Here actually, how, let me tell you, the thing is, I need to relate it the coordinate word. See, now let me tell you that here what is. Let me tell you differently than here. See, I have a vector, let's say 3, 5. I just wrote it as a 3 with respect to canonical basis 1, 0 plus 5 times 0, 1. Okay. So these coefficients are called coordinates. These coefficients are called coordinates. That's why here it is written as this one with respect to the canonical basis. Okay. Let's say I am writing 3, 5. Okay, with respect to the basis of 1, 0 and 1, 1. So we found a is equal to -2 and b is equal to some 5, I think. Yeah. Yes. So these are again the coordinate. I can write the same vector. This is what the change of basis is happening. This vector same written as a -2 and 5, but here the word with respect to the basis 1, 0 or on the basis. This is the same vector v. This is the same vector v, but this vector written with respect to the basis 1, 0 and 1, 1. This same vector v on the basis of this one look like this. Let me tell you the pictorial way it is. Let me tell you the pictorial way. So canonical basis is R. Okay. If you see the canonical basis is exactly this kind of space, means where the lines are intersecting like this, and 3, 5 is somewhere here. Okay, 3, 5 is somewhere here. But if you see this coordinate in place of like this, see like this, let's say like this here, R and R. A slightly modified here. Modified means here it is intersecting these two lines at the vertically horizontally, but here it is very slightly different. Some direction would be. So for the time being, let's say this represent your this R and this represent your this R. Here this one is representing this R, this one is representing this R. But here this one representing, let's say this one, and let's say I'm saying, even I'm not sure which one is representing, but for example I'm saying. So the same vector 3, 5 is here, but with respect to this basis, it could be here. Could be here. This is what it's happening, is change of basis in pictorial format. And these are called coordinate. So here this problem is find the coordinate of the vector of b with respect to this basis. Means here, if I will solve the first question, means here the first question is find the coordinates. Coordinate means I am saying this is your coordinate 1, 1. The a and b is called your coordinates. This a and b is called, and it asks that find the a and b. For this case, this is your first problem here, and for the second problem here, this one, for this one, it means that find the same vector on the basis of this 1, 2. Find your a prime plus b prime with respect to this. But the third problem is, let me take it copy here, then separately let me write here. The second problem, this one is find the coordinate v in the basis of this one. It means that this vector v is given in this basis. What it means that? It means that here v, which is your 1, 2, is given as 1 time 1, 1 plus 2 time 1 minus 1. That is the meaning of this vector v is given. This is the coordinates of it, and ask the find the coordinate with respect to this one. That means you have to find that this vector with respect to these coordinates, a time 1 1 plus a time 1 2, a time 1 2 plus b time 2 3. So what is the way to solve? Find, if you solve, if the vector is written here like this is the v on this coordinate, it means that if you solve this is going to be 1 plus 2, and it is 1 and minus 2, which is here 3 and minus 1. This, if you substituted there the value, the coordinates here, whatever the vector you got, this vector is the original vector. This is your original v given on the base. Now it will be on the basis of canonical basis. Now you have to solve this as a 3 minus 1. You have to find the value of here a and b.
Sir, like in the first question, it is written find the coordinates of v is equals to 1 comma 2 in the following basis. In the following basis means in 1 1 and 1 comma minus 1. If we take
this is what it is.
So it is
Correct.
also saying that 1 comma, we have to find the coordinates means a and b of 1 comma 2 in those given basis. And
For the second problem.
For the first problem.
First problem.
And in the second problem, if we just see until before with respect, so it is also saying find the coordinates of v is equals to 1 comma 2 vector in basis. What are the bases given? So we have to write v is equals to 1 comma 2 and we have to do the linear equation thing.
Yes, that is what it is.
But we are using v means vector as a and b. But
here is actually what is happening. No, here is it's hidden that v is given in the basis of this one. You want to find v on this basis. That is what it is, the question. It is given on in this basis. You have to find on this basis. This is the question. Your vector is given in this basis, so that's why in the basis of this one.
So that same thing is in the first question. We find the coordinates of v in that basis. It's same. Like we have to find the coordinates of that vector in those given bases. And here it is saying the same thing. You have to find
here it is saying before the with respect to exactly the same. That is what you are saying, no?
Sir,
But
so
here
I'm saying that we have to first find the coordinates of 1 2 in basis 1 comma 1 and 1 comma minus 1. Then we can use that as coordinates of the basis 1 comma 2 and 2 comma 3. But we did the opposite of that. Why?
find the coordinates of v in basis this one with respect to the basis of 1 2 and 2 3. One minute, I'm thinking to explain you. See, here is I will say, then it is not very much clearly written. It should be written properly. The vector v is given in this basis. Find the coordinate with respect to this basis.
Yes, sir.
So that is what here it's happening. That is the main confusion. This is what the main confusion is here. So here it is, it should be the vector. Here the modified question would be like this: vector v, which is 1 2, given in the basis 1 1 1 minus 1. Okay, find the coordinates with respect to the basis 1 2 and 2 3.
Yes, sir.
This should be a proper, like, this vector is given on this basis, you have to find with a different basis. Here the question is, find the coordinates of v in the basis of this one with respect to the basis of this. It is not
Yes, sir.
very, it is not, that is what I'm thinking. The question is given on this here, v is given on the, in this basis, we have to find the coordinate in this basis. Even if I will say that is what the, then it is not making so much clear. Yeah, this is not making your analysis more clear, not so much clear thing, because what it's happening, this vector is given on which basis and asking on which basis is not clear. Clearly it should be mentioned, the v is given in this basis, find the coordinate with respect to this basis. This is the simple thing. But here it is, then it is a bit confusion, because already the same coordinates is used and the same basis is used, and here it is asking, find the coordinates of v in this basis with respect to the basis of this one. Or maybe here some call will be there, something is should be more clear, but for the time being this should be. So that is what I am assuming. Here it is, it means that here that v is given in this basis, I have to find the coordinate with respect to this basis. This is what the meaning, which I am in free. And if it is clearly, if the proper question would be created, this is how it should be created. Okay. So for the time being you can leave, even if you want, then for the time being, even if you want, you can solve this the same problem. The problem would be like this: v is given in the basis of this one. You can solve even this. Now I hope, is this making clear to you? Is this making clear now, this question which I
Yes,
made
sir.
here?
Yes, sir. It's clear now.
V is given in this basis, we have to find the coordinate with respect to this basis, and we have to solve. So to solve this, this is the way it is. We have to first substitute the values. It is given with respect to this, so substitute, find that vector, and now with respect to that this basis, find the coordinates. This is how you can proceed. Okay.
Okay, sir.
So let's leave this problem, let's assume this problem, and do on this, because yeah, it is not now making, now you made this message. This is what I was assuming, and this is how I was doing. Now you emphasizes more, and that's why I started thinking how it is written. But yeah, something is missing in that wording, proper wording, where it is given and where you have to find, that is not clear. So to make clear, we can do it, because now it is, you can do it, this is a practice, so you can do it on this. Okay.
Okay, sir.
So I took a lot of time, many of you have leave now, so I don't know how it is first. So I have covered almost, not almost, everything of it. Change of basis, which is the peak of the basis finally, or peak of the week. Now basis, dimension, linearly independent vector basis, so many things we have covered today.
So now can you look on that practice assignment question number 7?
Okay. So the vectors representing the material requirement for product A and B are okay. You have to check it, that is this making independent or dependent.
Yes, sir. So
A
I
is
was
3 2. and 1 4. Yeah. And
was-
vector representing, yeah.
So I was getting the first answer correct, and it was showing the correct answer, but I'm getting also C option as correct.
C option. The span of vector representing the material requirement product A and B parallel represent all possible combination of materials, all possible combinations. That means here, if independent, if you are finding both are independent, right? A and B are independent, correct?
Yes, sir.
If both are independent, and then this should be correct, right? It says all possible linear combination of the material X and Y.
Yes, sir.
So that's why it is true. Are you getting it? Means all
Yes,
possible
sir.
linear. If two are independent, then these two are generated. A and B product can generate whole R2, right?
Yes, sir.
A
So
and B
in
product can
the
generate whole R2.
only A option is showing correct, but I
Oh, here,
selected
oh,
A and C.
oh, sorry. Yes, yes, yeah. So yeah, this is true, right? This is going to be true.
Okay, sir.
This is true. Yeah, right. You're right. Okay, that's all. So that's all from my side. Even any other doubt, any kind of, we have covered week one. But this is a base, okay? This week one is a base. Many things within it. If you understood week one, then done. Linear algebra half, almost part done. I tried my best to make you understand the all parts of whatever in week one. So many things covered in week one. Basis, dimension, coordinates, change of basis, even the main peak of it, change of basis. Okay, thanks. Thanks everyone for joining. Good night. We took a lot to discuss. Okay, it's going more
Thank
than
you,
this.
sir.
Okay, thanks.
Thank you, sir.
Okay,
Thank you,
thanks.
sir.